Okay, so welcome to Math 150 Multivariable Calculus. So what I wanted to do today is talk a little bit about the mechanics for the course. Given that this is the third calculus course that you're taking, there's already at least some motivation for why you are looking at this. But I want to try to get a sense of what particularly excites you. We have a wonderful opportunity here to structure the course based on what interests you. So I should, right now, you should have all received a link to the Google Sheet. I will, resend that later today. But what I want to get a sense from you is, two pieces of information. And, you don't have to answer it now, but do you plan on taking another math course after this? Yes, no, maybe. And if somebody has already answered, just increment the value by 1. And then what material would you like to see? Hopefully it will be related to mathematics and calculus. One year when I taught 150, somebody wanted to know more about bees. And so I'm always up for a challenge. I worked bees into the next lecture. You're welcome to put your name in. You can also just shoot me an email. But the goal is to try to personalize the class a little bit to what are you interested in, what excites you. Along these lines, if you want, you can do a project related to mathematics. It doesn't have to be entirely related to multivariable calculus for 10% of your grade. And this gives you a chance to try to explore something that you find interesting or fascinating. What I want you to get out of this is the ability to learn, the ability to present, the ability to solve problems. Most of you are not going to be using the specific material we cover in this course. Most of you are not going to be calculating partial derivatives 10 years from now. Most of you are not going to be finding areas under curves or volumes of rotations. But the idea of how to attack problems in general, that is going to be useful. Learning how to do some basic coding, that will be extremely useful. Along those lines, I do a lot of applied math projects with local businesses. If you have some coding skills, if you have some basic stat skills, there are a lot of opportunities, some of them just for experience, some of them paying very well. If you are interested in any of these, please let me know. I've been doing a lot of work with students over the past couple of years on a couple of lawsuits, including some from Major League Baseball, and have a lot of interesting stories I can share. You don't have to solve a problem fully. You just have to do a better job than is being done before. That is a much lower bar and a very attainable bar. And so the goal is by the end of the semester for you to have some useful experiences. So when you're trying to figure out what you might want to do next summer, or along those lines, you will have a good skill set. I used to tell students that if you had 3 skills, 3 classes, you would always have a job. And these were probability, statistics, and programming. And one of the big things in probability is finding the probability, the odds of something happening. We'll talk a little bit later today that a lot of that is related to integration. Integration gives us areas under curves. Curves are often used to represent probabilities. I can no longer promise this because someone did not get a job from her school a couple of years ago, and she actually sued her school. And she came up with a new type of discrimination, academic discrimination, that the school did more for students with higher GPAs than lower GPAs. So I unfortunately cannot promise that you will have a job if you have these skills. But what I can say is if you don't get a job, you will be the first student of mine in over 2 decades who is not able to get a job if you have these skill sets. And again, you don't have to apply them directly to a scientific discipline. If you have the ability to gather data, to analyze it, to present it well, this would be of great service in almost anything. So in terms of the mechanics for grading, I'm going to have you watch videos before class. And as long as you are watching the videos before class and coming to class prepared, 60% of your grade will be a 92.5%. So right on the board of an AA minus. So if the rest of your semester grades are an A, you get an A for the semester. If they're below an A, you have something pulling you up. And the reason I'm doing this is because I really want to use class time effectively. And so if everyone is prepared, we don't have to spend our time covering material that everyone had no problem with. Now, when you're watching the lectures, if there is something that you are unsure about, by all means, please tell me in advance, either on the Google Doc for the class, which I will set up later, or email me and say, hey, Professor Miller, I had a lot of trouble understanding the proof of the law of cosines or how we compute directional derivatives. Can you do some extra examples on that? Absolutely. But the goal of this is to use class time as effectively as possible so that if there are things that we're all really good on, we don't have to spend as much time on that. And if there are things that are causing a lot of trouble, we have more time for that. Obviously, the more you speak up, the better this is going to be for you. And this is both in terms of telling me in advance what topics you want me to cover, as well as when you're in class, answering questions and speaking up. So I like to ask a lot of questions throughout lectures. The next 3 or 4 classes, as we are in a semi-remote hybrid, may be a little bit different. But once we get back to being in person, I really want class participation for a variety of reasons. The first is, if you ever need a letter of recommendation, the more you speak up, the more I get to know you. So again, I'm always up for getting to know people. If you want to go for a walk, grab a coffee, grab a lunch, let me know. We can do it individually, we can do it in small groups. I always encourage students to try to get to know at least one professor well every semester. That way, by the time you graduate, even if you're only successful half the time, you'll have 3 or 4 people who know you well enough that they can write you a letter of recommendation, or that they will be thinking of you when they maybe get a job opportunity or they hear about something which is a good fit for you. I'm happy to be one of those people, happy not to be that person, but I encourage you, try to get to know at least one professor well every semester. The more you speak up in class, the more you come to get to know me, the better I will get to know you. So when you send me an email after class and say, hey, Professor Miller, these are the comments I made today, this just helps reinforce that connection. I put down good comments you make in a book. And so if you ever need a letter of recommendation, I have specific examples I can give, which makes the letter more powerful. And on that note, if you do think you might be needing a letter of recommendation from someone, it's often good to ask them after the class ends. Maybe you took a chemistry class and in the fall and you're going to be applying in the spring for labs. Ask the professor when everything is still fresh in their mind about what you did. And you're happy to talk with people about what's the right way to ask somebody for a letter of recommendation. So one of the reasons I want you to speak up is helps me get to know you, gives me good things to say about you. Another reason to do that is so that you gain confidence and the ability to be noticed. You are all smart, you all belong here, but there's a lot of people like that in the world. And because of that, it's very easy to get lost. And so there's a lot of very talented people whose names never percolate to the top. When I was in high school and college, I was absolutely terrified of speaking in public. And I always find it amazing that I now have a job where I have to be, in some sense, a professional lecturer. What really changed was when I was in grad school, one of my friends told me I should run for social chair. And I laughed and said, well, don't you want somebody who likes being with people to be a social chair? And she said, no, you'd be really good at it. And so that night at dinner, I asked my friends at the table, said, hey, if anybody's willing to do this with me, I'll do it. There's 3 positions. And one of my friends said, I'll do it. And it was one of the best things that happened to me. It really got me out of my shell. It got me comfortable speaking in public. So even if you think it's an easy question, just the more times you start to answer questions, the easier it gets, the more confidence you get, and the more likely you are later in life to be noticed. Related to this, sometimes people are afraid to speak up because they're afraid I'm going to show that I don't know something. Odds are, if you don't know something, you are not the only one who doesn't know it. Odds are, if you're confused about something, you're not the only one who's confused. There will be a large number of people who will be very grateful that you are speaking up, but you would never be able to tell by looking at them. So my first year at Williams, I was teaching differential equations, and linear algebra is not a prerequisite. And I wanted to do systems of differential equations, like, foxes and rabbits. How many rabbits and foxes will you have at a given moment in time? Well, the foxes parent the rabbits. The more rabbits there are, the more foxes can be produced because they have food. But the more foxes there are, the more rabbits that are killed, which makes it harder for the rabbits to be produced. And we needed a little bit of linear algebra, about 2x2 matrices. And I asked the class, does anybody want a review of 2x2 matrices? And there was silence. I said, everybody's comfortable with 2x2. Nobody wants a review. Okay, so back then we had clickers. This is what we did before people had cell phones and iPads and everything that allowed them to connect to the internet. And I said, I'm going to just ask, using the clickers, I'm not going to report the results to the class. I'm just curious. Press 1 if you want a review of 2x2 matrices. Press 2 if you don't. I never said I wouldn't tell other classes. I just said I wouldn't tell that class. 43% wanted a review of 2x2 matrices. 0% was willing to say they wanted a review of 2x2 matrices. So again, if there's ever something that you think I'd like to see more details, almost surely you are not the only person. I have taught multivariable calculus probably more times than years you've been alive. I have taught this class many, many times. I have lots of handouts, lots of materials. And we can do a standard class, but if there are things that you would like to see, we can absolutely try to work it in. If you are going to be going on and doing physics, and you want to make sure you see a little bit on the Green-Gauss-Stokes theorems. If you're going into economics, we're doing stuff on Lagrange multipliers, you want to make sure you really get a solid grasp on that. If you're going into statistics, we're going to do some stuff on linear regression and applications to curve estimation. There's lots of different topics we can do. So again, I hope you will reach out, we can find a time to chat individually, or if not, just shoot me an email about what excites you. And then we can adjust the course material a little bit to try to cover stuff like that. In terms of grading, I'm going to do an opt-out system. So I will assume that everybody is going to be watching the videos before class and will be coming to class prepared. 3 times all semester, you can tell me, hey, Professor Miller, something just happened unexpectedly. I wasn't able to watch the video today. I'm not prepared. And that's absolutely fine. As long as you let me know before class, that's okay. I'm not going to have you do a quiz or an assignment after each one to make sure that you are doing the videos. You're Williams students, you are on the honor code to let me know if you are not watching the video. In terms of exams, there will be a couple of midterms and then there'll be a final midterm. The final midterm you cannot drop, but all the midterms before the last, I will drop the lowest score unless you tell me otherwise. And there's many reasons to do this. One is we all can have a bad day. Another is on any test, I can only ask so many questions. The more questions I ask, the more accurate assessment I get of you, but that takes more time. Also, for some of you, it's been a while since you've done calculus, and so it could take a while for things to just get up to speed. So if you are doing much better by the end of the semester than you are at the start of the semester, I have no problems counting the beginning less and counting the end more. So unless you tell me otherwise, I will drop your lowest midterm score. I have been at schools where, interestingly, people have asked me not to drop the lowest score. So I will give extra credit if anybody can give me the reason why somebody would not want their lowest score dropped. It is a strange reason, but there was a logical reason. So at that school, an F did not show up on your transcript, but a C or a D did. And so for some students, they would rather flunk a course and not have it show up on their transcript and not count towards their GPA than get a C or a D. So you had actually created an interesting system where there was an incentive for people to fail a class. And the point of this is to always think about whenever you're doing something, what behavior are you encouraging? So is anybody familiar with the scandal in women's Olympic badminton from a few years ago? So a couple of years ago, one of the Chinese teams noticed that if they won the game they were playing, they were going to have to play another team from China in the next round. But if they lost, they could make sure they didn't play a team from their country. So they deliberately played to lose. They deliberately missed the birdie. They deliberately hit the birdies into the nets. You can imagine how happy the fans were who paid good money to watch an Olympic badminton game were to see this. Once they started to lose, other teams said, okay, we can play to lose as well. And you had, I think, 3 other countries deliberately playing to lose to adjust where they would be seated. People had warned the committee beforehand that they had created an incentive structure where it could benefit some teams to deliberately lose. In the end, the 4 countries were disqualified for their behavior. And I think it was under some kind of sportsmanship clause that was used for that. But just as an interesting thing to think about, there's always unintended consequences. Try to think as much as you can about what are you setting up when you do things. So these are the course mechanics. There will be homework due for the most part after each class, and it's due at the start of the next class. And then the graders will return the homework by the next class. You are welcome to either do it by sending a PDF or by handing it in person, whichever is easier for you. What I am going to do for the first few homework assignments, since we are not meeting in person, is the first few homework assignments will all be due on the Monday when we come back and start meeting in person, except for a short email assignment I want you to do for me. I do not encourage you to wait until the last minute to do all the homework. Start working on it as you can. But as we are not meeting in person, with all the different systems and whatnot people can have, this way you all have an extension on the first few assignments to the first day we all meet in person. During the semester, if something comes up and you need an extension, as long as you ask me at least a day in advance, it's typically not a problem. If you ask me less than a day in advance, you need to have an incredibly good reason as to why. You need to be budgeting and you need to be planning ahead. Since the videos are going to be posted, you are welcome to do some of the homework or do the readings and videos a little bit in advance if you want. That's absolutely fine. I strongly encourage you to work in groups. If you're having trouble finding somebody to work with, you can just email me and I can keep a list of names of people who are looking for partners and try to help match people up. Just write on your homework, I worked with so-and-so. And again, strongly encourage you to do that. I will also drop whatever homework assignment helps you average the most to have dropped, which is not necessarily the homework you did worse on, because not all homework assignments are worth the same number of points. Okay, any questions on the mechanics up to now?
Is there TAs for this class?
Yes, so thank you. So we have 2 TAs for the class, and we have structured it right now so that tentatively they're going to have extra office hours on Tuesdays, Thursdays, and Sundays, the day before homework is due, and then less, but available on Mondays and Wednesdays. For now, I'm not having them do office hours on Friday or Saturday. Based on historical data of Williams students, I am assuming that Friday and Saturday is not the ideal time to have office hours, and it would be better to have extra office hours on Tuesday, Thursday, Sunday. But if people do want office hours on Friday, Saturday, just let me know. We're not going to finalize everything for at least a week or so. We should hopefully be starting office hours this Sunday. And the reason I don't want to finalize everything right now is a lot of people's schedules are still in flux where you don't know what classes you're necessarily going to be taking. And because of that, I want to wait a little bit and give everybody a chance to figure out what classes you're taking and what your schedule looks like. And then if I'm in my office, it's office hours. Your best way to reach me is by email. And then if you want to get together either individually or in small groups, just email me and we can find the time to do that. But there should be plenty of resources and hopefully adjusted at times that will work well for you. And if there's not, let me know and we can try to adjust things to make sure that somebody is available when you want to chat. Other mechanics questions? Okay, so I'm going to assume again an opt-in system that unless you tell me otherwise, I'm assuming everybody's going to be coming to class prepared and everybody wants to have their lowest midterm dropped. All right, so what I want to do now is just talk a little bit about some of the motivation for what's going on. So because this is Calc 3, you've done Calc 1 and Calc 2. Although for some of you, it may have been a while since you've done that. And so the question is, what are the big problems we study in Calc 1 and Calc 2? Well, Calc 1 is about derivatives. It's about how things are changing with time. So maybe I have f of x tells me where I am at time x, and f prime of x will then tell me how fast I'm going. And then after that, the next thing is integration. It's finding the area under curves. So I mentioned this earlier. Does anybody know why we care so much about areas under curves? So we only have so many, classes to do. Why are we spending so much time?
Integration shows us, I guess, accumulation.
So accumulation, good. So what might we want to know that's accumulating?
In physics, it can be used to find distance.
Okay, in what sense?
Well, if the equation of the curve is a position equation, then, or not a position, a velocity equation.
It's a velocity equation, yes, excellent.
Yeah, using the area under the curve gives you how far the object has gone.
Good, so it's always worth understanding what is the inspiration. So a lot of mathematics has been developed by physics, and a lot of this has been developed by a quest to understand the cosmos. So if people are interested, I don't know if we can do it, but in previous years, I've talked to the rare books librarians here, and Williams has a phenomenal collection of first edition books. They have a first edition Newton's Principia, where calculus was first written down. They have first editions of Galileo, Copernicus, and whatnot. And the desire to try to understand the orbits of objects was a huge push to understanding and developing mathematics. But another one, which I talked about briefly, is probability, is to try to find odds of an event. So when you hear probability, what do you think of when you hear probability? First thing that comes to your mind when you hear probability.
The likelihood that an event happens, and so the area
Good.
under a curve could give you the probability.
Excellent, likelihood. So what are the likelihoods? What possible values can you get for a likelihood?
Zero to one. Yeah.
0 to 1. And when you say 0 to 1, it's 0 to 1 inclusive, from 0 to 1. So no matter how bad you are, and we have some very bad sports franchises, you're never going to have less than a 0% chance of winning, and you're never going to have greater than 100% chance. Your probabilities are between 0 and 1. And in a lot of situations, we can represent a continuous event by a curve. And so, for example, if I give you some curve, say f of x, and it has maybe a couple of different regions where it's defined, if f of x is greater than or equal to 0 and the area under it is 1, then it's a probability distribution. And then the probability we take on a value between a and b is just going to be the area under the curve from a to b. And it's important to note that there's a lot of processes that start off simple, but after a few iterations become very complicated. And we often want to understand what's going on in the limit. And a lot of calculus is about what's going on in the limit. The very definition of the derivative, it's the limit as h goes to 0 of f of x plus h minus f of x, the change in f divided by h, the change in time. So when we think of discrete events, the two ones that people often think about is a fair coin and maybe rolling a fair die. So if you have a fair coin, you have a 50% chance or 0.5% or 0.5 that it lands on a head, 0.5 that it lands on a tail. For a die, if you roll a fair die, then the probability you get a 1, 2, 3, 4, 5, or 6 is 1/6, and the probability you get anything else is 0. So these would both be examples of a uniform distribution. All the possible events have the same probability. And then you can look at more complicated processes. So imagine we rolled 2 fair die, and we ask, what is the sum? So do you think that this is going to be uniform? Do you think all the possible outcomes will be equally likely? And what are the possible outcomes? So if I roll 2 fair die, what are the possible values for the sum?
From 2 to 12.
From 2 to 12. And do you think all of these are going to be equally likely?
No.
No. So what's the probability we roll a 2 or a 12?
One 36.
136. There's only one way to do it. And the probability that we roll a 7 is actually going to be 6/36. You could write down all the different possibilities, or a faster way is to just say, well, wait a minute. No matter what I roll on the first die, there's one and only one value on the second die that's going to make the sum equal to a 7. So really, the first die doesn't matter. I can just view it if I want to get a 7, there's only 7. I'm sorry, there's 6 ways to get the 7. And if I do a little plot, you can actually show the probabilities going up. It's 1/36 for rolling a 2 or a 12. It's 2/36 for rolling a 3 or 11, 3/36 for 4 or 10, all the way up to 6/36 for rolling a 7. And so now we have a more interesting probability distribution. It's no longer uniform. And so one of the big desires in calculus is to find areas under curves. If you took Calc 2, your professor might have told you the great lie. And the great lie is that you leave Calc 2 feeling that you know how to do integration, but you can't. You can't really integrate in general. I can't, nobody can. Integration is hard. Differentiation is very easy. If I give you any combination of the standard functions, no matter how painful it is, you may not enjoy it, but you can find the derivative by just constantly applying the rules of differentiation. All right, I've got a sum, I've got a product, I've got a quotient, I've got a power, I'm chaining, I've got a multiple. You can just keep whittling away. And it may take a while, but I can't give you a function which you can't find a nice close form of the derivative. Integration is the opposite. Unfortunately, most functions don't have a nice antiderivative. They don't have a nice integral. Fortunately, there are large classes of functions that have nice antiderivatives. And it turns out that these are often very flexible, and you can model a lot of things in the real world with them very close. And again, for a lot of applications, it doesn't have to be perfect. It just has to be pretty close. So later in the semester, I will be giving a lecture on applying calculus to baseball. And for those of you who are baseball fans, if you know about the Pythagorean, expected won-loss record, I am the person who came up with the theoretical justification as to why that works. And this is one of the statistics that is prominently displayed on most expanded standings pages. So it's a statistic that is quite important, and there's a nice justification as to why it seems to be applicable, coming from looking at finding areas under curves and finding probabilities. And so we need to model the run distribution of teams. And there are some nice probability distributions which have tractable integrals, which do a really good job of approximating all of this. All right, so this is one of the major themes. Now we are doing multivariable calculus. So that's basically just doing calculus many times. So what we're going to do is we're going to be looking now at functions of several variables. And there's a lot of different applications we can do. So you might remember one of my favorite problems in Calc 1 is the Farmer-Brown problem. So does anybody remember the cows and pens problem? So the Farmer-Brown problem is the following. Let me just get to a blank page. So Farmer-Brown. You have some pen, and maybe you have 40 meters of fence. So the semi-perimeter is 20, and you want to maximize x times y. And so for a given perimeter, what is the largest area rectangle you can form? And the way we solve this is, well, if x plus y is 20, then that means we can solve for y in terms of x. And we get that y is equal to 20 minus x. So we want to maximize x times 20 minus x. And now we can use techniques of one variable calculus to solve something like that. But really, it's a constrained optimization problem in several variables. I have two variables, x and y, and I want to maximize the product of x and y subject to x plus y is 20. If I want to generalize this to maybe I want to build a box and I have so many square meters of sheet metal to use, what's going to be the greatest volume if it has to be a rectangle? Why might you be making things in rectangles? Because a sphere is going to have a greater volume for a given surface area. Why might you use rectangles? So any thoughts as to why we might use a rectangle in the plane rather than a circle, or a box in 3 space rather than a sphere? You'll get more area, you'll get more volume if you use the circle or the sphere. Why would we use a rectangle, or why would we use a box? So if you think about the process of actually making things, it's much easier to make a rectangular pen or to make a box than it is to make a circle or a sphere. If you think about stacking things, it's definitely a lot easier to stack boxes than to stack spheres in terms of wasted space and whatnot. And so when you are trying to optimize, you have to be very careful that you optimize across all the things that really matter. Next year, I will probably be teaching a class in operations research. One of the most famous problems is called the diet problem. What do you think the goal of the diet problem is? Anybody want to guess what you might be trying to minimize or maximize if you are, say, the ruler of a country and you're trying to decide what crops to grow?
Maybe maximizing calories per acreage.
Yeah, maybe maximizing calories per acreage. And so related to that could be minimizing the cost to keep people alive. Maximizing calories per acreage, I think, might actually be equivalent to minimizing cost per diet that will keep you alive. So when I taught operations research years ago, some of my students did a project on this, and they went to Stop and Shop's online website, and they downloaded the nutritional value of every product, and they came up with a diet that would keep you alive with the fewest calories available locally. And they made it and they brought it to a class for me to eat. Sadly, I was on some medication at the time and I wasn't sure I could risk eating that with the medication, so I regretfully declined. But why might I not be so eager to eat that? They gave me a diet that would keep me alive.
Because it would react poorly with the medication you were taking.
That was what I said to them, and I'm sticking with that story. It's a shame I can't bring to Zoom the smell of what they brought. Why might I be a little bit hesitant to eat it?
Because it was gross.
Probably pretty
Oh, it was
unappealing.
disgusting. Oh, it was disgusting. I mean, hats off to them. This was Williams students at their best. This was an A+ presentation. It was disgusting. So when you're trying to keep people alive, okay, step one is to stay alive. What might be another thing that you might be a little bit concerned about?
Might not be super healthy, even though it's keeping you alive.
So there's that. But after health, what might you be concerned with?
Taste.
Taste. And so then you might want to have a more interesting, I'm willing to pay a little bit more for something that tastes a lot better. And then how much more are you willing to pay? Right now, we have a problem like this going on in terms of the response to the COVID epidemic, pandemic, however you want to phrase it now. What are we willing to do? What are the trade-offs? We can have very strict COVID policies that will maximize the chance of people surviving COVID or minimize the chance of getting COVID, but it will have a lot of other costs. There'll be the social emotional costs. There will also be the increased deaths for people who are now suffering from isolation, not getting the medical treatment they needed. And this happened at during the lockdown. And so when you have these optimization problems involving several variables, it becomes extremely complicated. And you have to really think, what am I trying to maximize? What am I trying to minimize? And the larger the system, the more complicated it is, the harder it is to study. So a lot of what we're going to be doing in multivariable calculus is we're going to try to build tools to do mathematical modeling on things that depend on many different things. And so I'm going to just end today with a motivating example. So when I was an undergraduate, I was a double major math and physics. And so my go-to examples are always going to be physics and sports. But again, if there are other things you want to see, somebody wanted to see bees one year, just email me and happy to bring them in. So I want to talk about a motivation from Newton. So the motivation is that when you're trying to figure out what's going on with gravity, you have to figure out the force of attraction between every two atoms of the two objects. If you have the sun and Mars, you want to calculate all of those interactions. And then somebody said earlier that integration is all about adding things up. And you add up all of those contributions. And Newton's great insight was that you could assume that all the mass of the sun is at its center and all the mass of the planet is at its center, and reduce it to just 2 points and calculating what's going on in a much, much simpler case. And so the big thing he had to show was that you could assume all the mass is concentrated at the center. Now, you must be very careful when you make assumptions, and you want to prove things. And we'll see a little bit later how dangerous this can be. It turns out if you have a point mass inside the sun, it does not feel the effect of all the mass of the sun at the center. It only feels the effect from all of the mass that is at its height or closer to the center. Anything that's outside of it in a ring actually balances out and doesn't contribute. All right, so going into details, Newton's famous law of gravity is that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of their distance. So what this means is if we were to double the distance between 2 points, the force would be 1/4 as strong. If we were to triple the distance between them, it would be 1/9 as strong. And as an aside, this assumes the force acts instantaneously. A lot of other wonderful things you can say, but first, we just want to see, can we assume all the force is coming from an equivalent body where all of its mass is at the center? So one of the types of arguments you want to learn how to do is called the without loss of generality. So without loss of generality, we want to say we can assume that all of the mass is at the center. Well, we're going to prove that. But if we want to prove that, we have to look at all possible placements for the second object. And then we say, well, without loss of generality, let me choose my coordinate system so that the second object is at the North Pole, is just above the North Pole. And this is a really nice simplification. So the laws of physics should not depend on how I choose to orient my coordinate axis. And by doing this, I just have a little bit easier coordinate system. I could, of course, do it in a more general coordinate system, but this is going to make the calculations a little bit easier. So what we want to do is we want to replace the complicated sun's continuum with a discrete set of points. We're going to choose points in a lattice. And the smallest separation we have between the lattice points, the better approximation it's going to be for a sphere. So if we take only 4 or 8 or 16 points to approximate the sphere, it's not going to be so good. If we take on the order of 1 million or 1 billion, we're going to maybe miss a few on the boundary, but it's going to be pretty close. And so as an example, if we had a cube, this would be a simple cubic lattice. We put a mass at each of these, and as you go left, right, up, down, forward, back, you're always moving the same distance. And the smaller gaps we have, the better approximation we're going to have for what's going on. And so if we have n points and we have a mass of, say, 1 sun, each object would have a mass of 1 over n. And the hope is that as we take the limit, as the mesh becomes finer and finer and finer, that this will converge to being the same contribution as if all of the mass were at the center. All right, so we want to write a little computer program to actually do the calculations and compare. So I wrote the program in Mathematica. It's not that long to do. It simplifies the things a little bit to notice that a lot of points are going to have the same contribution as other points. So I can just put in some multipliers. But this is just programming a little bit more efficiently. And so what I did is I chopped things up and I moved plus or minus 40 in each direction. And I put down the points and I said, okay, which points are inside the sun, calculated the contribution. And then the left plot shows you what is the force from the discrete approximation versus the force from assuming all the masses at the center. And the x-axis is different distances, 1 unit, 2 units, 3 units, 4 units, and so on. And I plotted both the discrete and the continuous on the same curve, on the same plot. And if you look, you really can't see a difference between them. The points look like they are perfectly matching. And so whenever you have things that are very close to each other, what you should do is you should plot their difference. And so the right-hand side is a plot of the difference between them. So it's sort of maybe -6 times 10 to the -6, and it's going down to very close to 0. So does anybody know roughly what is 10 to the 6? What unit is that? What number? So how big is 10 to the 6?
100,000.
I'm sorry?
100,000.
Not 100,000.
Is it a million?
It's 1 million. It's 1 followed by 6 zeros, so it's 1 million. So if you want to try to get a sense of what is 1 in a million, I think I heard that there's about 1 million words maybe in the first 5 Harry Potter books. So that would be equivalent to something happening with chance 1 in a million. I circle a word randomly in the first 5 books. You circle a word randomly in the first 5 books, and we chose the exact same word on the exact same page in the exact same book. To just give you a sense of just how likely 1 in a million is. So what we're seeing is already with just 40 divisions, it looks pretty close. The error is really small. So the question is, if we go further and further, will the error go to 0? Or is there fundamentally a difference between the two? And again, unless you can go further, it's unclear what's going on. It turns out for this problem, the error does go to 0, but that's not always the case. And the example again from physics is Einstein's theory of special relativity. And so classically, if you had a train going at 100 miles an hour and you were running on the train at 10 miles an hour in the same direction, someone on the ground would say they see you moving at 110 miles an hour. And as a first estimate, that's not bad. But it turns out it's not correct. There's a small correction. You have to divide the sum of the speeds by 1 plus the product of the speeds divided by the square of the speed of light. Well, the square of the speed of light, that's pretty large. So the speed of light is about 186,000 miles a second. The fastest man-made objects, we're probably talking about some of our rockets going on the order of 25,000 miles an hour. A train and a person is much less than all of that. And so the problem is, if you look at the difference between just summing the speeds and taking into account the correction, it's going to be on the same order of magnitude as an error on the size of 1 in a million, which is what we were seeing in the approximation. And this is what I mean about being careful about what assumptions, what conclusions you draw from things. So on the left, I'm just plotting the difference between the Einstein correction and the classical prediction for adding two speeds. If you're traveling on the order of a couple thousand miles an hour, it's very similar to the order of magnitude errors we had in approximating with 40 points in each direction. The error starts to get very significant as you start getting close to the speed of light. So the whole point of this is to just give you a warning about how careful you have to be. So one of the big goals is to actually be able to use the tools for multivariable calculus to attack problems we care about. And for those of you who are doing physics, this is one of the most important ones of all time, that we can assume that all the mass is concentrated at a point. All right, so this is a good place to stop. I'm going to ask if anybody has any questions before we adjourn.
I was looking over the website. And I'm just kind of confused about due dates because it seems like they're from previous year.
I haven't put in the due dates for this year yet. Those are last year's due dates.
Oh, okay, but that will change.
Yep, that will change.
Oh, okay.
And so I'm changing things right now because of the first 4 days being remote. I have decided not to have homework due for the first for the next 3 classes, except for one email that I want you to do, is I'm going to adjust the due dates. So it's not going to be exactly the same as last year because of the remote stuff.
Okay, thank you.
Yep. Any other questions?
I'm having a tough time accessing the spreadsheet you just sent out because it's asking me to verify an email that I don't have access to.
All right, so then just shoot me an email and I can try to add you.
Sick, thank you.
Yeah, it's the same for me as well.
I
I
also
also have
have,
that issue.
Yeah, same.
Me too.
Second.
All right, so if you're having trouble, I put everybody's email from Glow into the Google Sheet, but sometimes it wants me to just add it again. So just send me your Williams email and make sure, if you have 2 different Williams emails, sometimes you have your full name and your shorter Unix, send them both to me and I'll put both of them in. Okay, any other questions? All right, have a good day all. Take care.
Thank you.
Thank
Thank you, Professor.